Okay, the last topic in this section is something called the rank nullity theorem. And it says that if T is a linear transformation from V to W, then the dimension of the kernel plus the dimension of the range is equal to the dimension of the domain, also known as the dimension of V. And basically the reason this is called the rank nullity theorem, we've talked before about the fact that the kernel is also called the null space, and so the nullity is the dimension of the null space. The range of a matrix is also called the rank of a matrix. And so this is basically saying that the nullity plus the rank is equal to the dimension or the size of the domain. And what I thought I would do is go through the examples we've looked at so far in this section and just try and understand what exactly this is saying. So the first example we looked at was the derivative going from P2 to P1, which is a three-dimensional set into a two-dimensional set. So this is 3D, this is 2D. But if you look at your kernel, it has a basis that's one-dimensional, so nullity is 1. Your range is two-dimensional, and so your rank is 2. So 1 plus 2 should be 3, which is the size of the domain. So 1 plus 2 equals 3. Sounds okay. Okay, maybe a better example. The function we looked at that went from P1 to M22, we didn't actually find its kernel and range, but I've written them out. The kernel, there actually aren't any vectors that get sent to 0 other than 0 vector itself. So that's a 0-dimensional null space, or the nullity is the number 0. We have a 2-dimensional range, so 0 plus 2, and 0 plus 2 should be 2, which is indeed the dimension of the domain. P1 is 2-dimensional. It's all things that are multiples of x's plus constants. Next example we looked at was this T going from xyz into x minus y0. We did find the kernel and range for that, and notice the kernel is 2-dimensional. It has 2 vectors in it, so nullity is 2, and then the rank, this dimension, the number of vectors in the basis of the range is 1, and so we have 2 plus 1, which is also 3, which is the size of our domain. Reason this is useful is that we can either use this to confirm to ourselves that we're doing this right, or if we know the size of 2 out of the 3, we can say what the size of the other one is. So like if I told you I have a 2-dimensional kernel and my domain is 5-dimensional, then okay, the range must be 5 minus 2 is 3. Okay, the last example we looked at was the one defined by a matrix. That was a 2x4 matrix. We found a basis for the kernel and the range. We also said that the kernel of the transformation is the same as the null space of the transformation, which is also the null space of the matrix. The range of the transformation is also the column space of the matrix. And we've touched on this before. The column space is the same, the dimension of the column space is the same, how to do brackets. Dimension of the column space is the same as the dimension of the row space, which is the rank of A. That's the reason why this dimension of the range ends up being the rank, is that it's a column space of the corresponding matrix, which is the same size as the row space, and the size that is called the rank, which is actually the number of leading ones. So the number of leading ones was dimension of the row space. That was also the rank. And so the fact that we have 2 leading ones tells us that the rank is 2. So for this case, that's 2. The null space is the size of our kernel, the size of things that get sent to 0. And so basically that's the number of free variables. And since we have 2 spare columns, we have an S and a T, this is saying that our null space is also going to be 2. And so if we add those two up, rank plus nullity should add up to the dimension of the domain, which is 4. But notice the way I've drawn it here in terms of everything related to columns. we have two columns that correspond to the column space or the rank or the range. We have two columns that correspond to the nullity, and that should add up to the total number of columns. So realistically, if we think back to matrices, we can think about this nullity as being the number of columns in reduced row echelon form that don't have leading one, plus the number of leading ones adds up to the total number of columns, which we've seen some variation of that theorem before.